Okay, so we're gonna start in a few seconds, so.
Okay, so I think I need to say got it, right? So they
Yes.
can record.
Yes. Okay, so thank you very much for coming. Hopefully no one thinks that the seminar is happening in the library space. This was just a temporary solution. Right, so today we're very excited to welcome Andra Stroe. Andra is an astrophysicist at the SAO and an associate astronomer at the Space Telescope Science Institute. Andra's scientific interests revolve around understanding the physical processes that regulate the interplay between large-scale structure, galaxy formation, and black hole evolution. Andra combines panchromatic observational data and modeling of galaxy clusters to piece together the star formation, black hole feeding and feedback, gas inflow and outflow, and structure formation puzzle. Andra is also interested in the evolution of galaxies and AGN from the perspective of cosmic evolution, with a window towards high redshift clusters and protoclusters. Before taking up her current roles, she held the Clay Fellowship at the Center for Astrophysics, Harvard and Smithsonian from 2018 to 2024, and she was also an ESO Fellow at the European Southern Observatory headquarters from 2015 to 2018. She completed her PhD at Leiden University in 2015. So today she'll be discussing a low mass merging galaxy cluster with the exception in the existent radio relics. So thank you, Andra, for accepting our invitation, and take it away.
Thank you so much for the very nice introduction. Thank you to the organizers for, providing me this forum to tell you about this very, very interesting merging galaxy cluster that together with my collaborators, we did kind of a very extensive analysis of. Because this was a multi-wavelength analysis, it required expertise from many different people, many of whom are here at SAO. And, before I get into it, I would like to particularly highlight the early career scientists who led and contributed to this work. Andra Stroe, who's a postdoc, and she's here in the audience, who led the radio work. Zhenlin Zhu, who contributed a lot to the analysis of the X-ray data, and Yunmo An and Wonki Lee, who worked on the weak lensing and simulations work as part of this collaboration. But, before we get into it, I would just kind of like to share with you my excitement for the field of galaxy clusters and to tell you that, over the past 10 years, the number of detected galaxy clusters has really increased exponentially because of all of these, fantastic new instruments that have come online. And it's a really great place to be also for the future. In the next, few years, we expect a treasure trove of galaxy clusters of lower masses and also higher redshift to be detected with the instruments that are just recently flying, like Euclid, or instruments that are soon hopefully going to be launched, like Roman, and also in the more distant future, thinking about Athena. And one of the main realizations that we've had with these larger samples of galaxy clusters that we've gathered is that clusters tend to come in two major flavors. And probably most of you are familiar with relaxed galaxy clusters, the objects that are virialized. And, we believe that they're kind of fully settled and they haven't had any recent activity or interaction. And this leads to generally a very smooth and featureless intracluster medium. And also the galaxy populations are very typical, they're very red, consisting of many passive dead elliptical galaxies. Now, on the other side, we have merging galaxy clusters, and these are more interesting. They're objects that are actually undergoing an active growth phase. So imagine two clusters colliding with each other to form an even bigger cluster. And as you can imagine, this is a very energetic process. It's actually the most energetic process is the Big Bang. 10 to the 64 ergs are being released into the intercluster medium over, timescales of 1 billion years. And this leads to a very kind of messy, complex X-ray morphology in the cluster, and also galaxy populations that are a bit more special and tend to be more blue, actively star-forming galaxies. And, with these larger samples, what we've realized is that even at ratios below 1, a very high fraction of clusters are actually undergoing mergers. And particularly, thinking that every local cluster has undergone at least one merger in its history, it really shows us how important it is that we study these merging clusters to the same level of detail that we have managed to get in relaxed clusters, to be able to get a complete picture of the cluster population. And, I've been talking about these mergers, and just very quickly, I would like to show you some snapshots from a simulation showing you in a very idealized scenario what we believe happens. You have two objects kind of coming towards each other, and they pass through each other. And then obviously, once they pass through each other, you see there's a lot of disturbance. The two subclusters are mostly, completely destroyed. And then at the very end, you get a single kind of object that's very messy. And what we believe happens when you have all of these disturbances is that you get a lot of shock waves and turbulence that is released into the intercluster medium. And this is kind of similar to what happens when you have an object, a dense object going through a medium. You form a lot of turbulence in the backflow, and also you expect to form, discontinuities, shock waves as well. And we think that a telltale sign of the presence of these shock waves and turbulence, these non-thermal phenomena in galaxy clusters that are emerging, is this diffuse radio emission. And it tends to come in two major flavors. On the one side, we have radio relics. These objects are megaparsec sized. They're diffuse synchrotron sources that are located towards the cluster periphery, and they generally have no optical counterpart. But they're also very strongly polarized. So this is why we believe that they are associated with these shock waves that are produced when the clusters merge with each other. The shock waves travel through the intercluster medium and accelerate particles from the intercluster medium, which then in the presence of magnetic fields produces this synchrotron emission spanning megaparsecs in the cluster. Now, on the other side, we have radio halos, and they're also diffuse, but they tend to be located towards the center of the cluster, and they actually tend to follow the distribution of the intercluster medium, kind of the X-ray contours. And they're also unpolarized. So we believe that these objects are rather, they're not formed via shock waves, but rather from turbulence that is reaccelerating particles, electrons from the intercluster medium. And, we've made great strides in the field over the past, 10 years to really understand the physics that is at play in producing these diffuse radio sources, but there's still some very big challenges and big questions in the field, particularly to kind of obtain models that are, can explain all of the observables in a self-consistent manner. And, according to the most widely accepted scenario for radio relics, they originate when particles are accelerated at these shock fronts via the diffusive shock acceleration mechanism. And this might be very familiar to those of you who work more like on supernovae. It is the same scenario that is, let's say, proposed for why particles are accelerated there. But the difference is that in these cluster shocks, their Mach numbers are much weaker. We are talking about Mach numbers of 2, 3, 4. And theoretical work has shown that it is quite difficult to explain the amount of radio emission we have at these shocks that are very weak, because the acceleration efficiency is too low if you are accelerating particles directly from kind of the thermal pool that is available in the intercluster medium. So there's some, alternative models that propose, okay, maybe actually this shock is just reaccelerating particles. So, the particles might have been pre-accelerated by some AGN, or maybe you have a scenario in which there's multiple shocks going through the same region over and over again, and, energizing, re-energizing, further energizing these electrons. Now, on the side of the halos, because they we expect them to be correlated with turbulence. One of the questions is exactly, okay, when is this turbulence being produced? When is it kind of peaking? Are the halos kind of becoming brighter and then fainter as the turbulence goes up and down in these merging clusters? And one of the parameter spaces that hasn't been very much explored is the low mass regime for the mass of the galaxy cluster. And why is this important? Models and simulations and also some observations are showing us that the fraction of clusters that hosts radio relics increases as the mass of the parent cluster goes up. So, if you think about clusters that are above 5 times 10 to the 14 solar masses, about 40% of them actually host radio relics, whereas only about 14% of those that are above a mass of just 10 to the 14 host radio relics. But these models, they're very sensitive to exactly which fractions we're talking about. But as you can see, we don't have a lot of objects with low masses that we've looked at. So it's really critical to kind of improve the statistics at these lower masses so that we can better constrain particle acceleration as well. Now, in terms of the radio halos, we know that the radio halo power actually increases with cluster mass and X-ray luminosity. So it has been challenging to observe these kind of very faint halos that you would expect at the lower mass end of the cluster mass distribution. And we only actually have a handful of radio halos detected in clusters with masses below 5 times 10 to the 14. So again, if we could get more clusters at this lower mass, it would be really every new detection is very, very significant. And a particularly kind of special class of clusters that are hosting radio relics are those that host double radio relics. So that means, imagine 2 radio relics almost symmetrical on either side of the merging cluster. And simulations have shown that only about a third of clusters that host radio relics host a double radio relic system. So they're very rare. And also in observations, we only have about 30 clusters that host these double radio relics. And why are they so special? Is because they require particular conditions to form. So in order to get, 2 symmetrical shock waves on either side of the cluster, kind of the most ideal scenario for that to happen is if you have a merger between 2 clusters of almost equal mass. So that gives you a lot of insight into the merger history of the cluster. And also ideally, you would want this merger to happen in the plane of the sky. So you detect, it's kind of an observational selection as well. If the merger is happening in the plane of the sky and you have the radio relics, you see them edge on, you have the widest, kind of the highest chance of detecting it. So these double radio relic systems offer us this unique opportunity to pose tight constraints on particle acceleration mechanisms in the context of the very well understood merger scenario. And particularly kind of as a second step and as a bonus is if you have, a comparison between double radio relic clusters that also have a halo and compare them to those that don't have a halo, you kind of have this ideal test bed for constraining what are the actual cluster properties that are most important for governing the formation of these radio halos during the merger. And one of the objects that we thought would be super, super interesting to look at was this PSZ telephone number cluster. And this was, it really piqued our interest. We looked with LOFAR, as a low frequency, high sensitivity, good resolution radio telescope. It did wonderful surveys of the sky and it picked up a lot of very, very interesting objects and detected many new clusters with diffuse radio emission. But this particular one was really kind of struck us as a great environment to test particle acceleration in a low mass plasma and a low plasma density regime. And why do I say that? Well, the cluster based on Planck observations, we expected to have a mass of about 4.2 times 10 to the 14 solar masses. So it's a relatively low mass cluster at redshift of about 0.2. And you might notice these kind of arc-like patches of radio emission that are highlighted in green on either side of the cluster. And these are 2 radio relics. And, they have very typical kind of luminosity and sizes. But what is very interesting interesting about them is that they are located exceptionally far away from the cluster core. So they're about 1.1 megaparsecs in projection, very close to the R500 of the cluster. So, the question is, okay, we have these very bright radio relics in this very low mass cluster at very large cluster-centric radii, where you actually expect the plasma density to be quite low. So how can you get so much radio emission so far away from the cluster center where you just don't really have a lot of particles to accelerate? So, we thought, okay, maybe the relics are associated with very, very strong shocks, like maybe the shocks are like 5 or something. Or maybe the cosmic ray density is higher than we expect because the cluster is more massive than we expected. Or maybe it's a bit more of a, more complex merger, and, that kind of explains the location of these relics and also some of their morphological properties. And, together with this dream team, we put together these multi-wavelength observations, and we explored this cluster in a set of 3 papers that were just accepted to AppJ about 3 weeks ago. And the first paper of the series focuses on the X-ray observations. This is the paper that I led together with Kamlesh. The second paper focuses on the radio properties of the diffuse sources, and this was a paper led by Kamlesh. And then the weak lensing analysis of the cluster and the simulations aimed at understanding the merger history of the cluster were presented in the paper led by Yunmo An. So let's delve into it. We put all of this data together. What have we learned about this interesting cluster? And the first thing that really struck us was that both the X-ray observations and the weak lensing observations tell us that this cluster is actually even lower mass than we had anticipated. The X-ray puts the mass at about 2.3 times 10 to the 14 solar masses. So this is a very, very small cluster with an R500 of only about 0.9 megaparsec. For the trained eyes in the audience, you might already notice in this X-ray image that there's 2 peaks. So we were very, very confident that this is actually an emerging cluster. With, the 2 peaks indicated, it's most likely 2 main subclusters that participated in this merger. And the mass ratio between them is very close to 1. It's, between 1 to 1.1 to 1 to 1.4. So this kind of all makes a lot of sense with these 2 radio relics that the clusters have similar masses. Now, we also looked at the thermodynamic properties of the cluster, and kind of some of the insights from here is that the northern core and kind of this bridge of emission that connects it to the southern core is, there's some of the coolest areas in the cluster. So this might tell us that this was a cool core cluster, and this core was disrupted, I should say, as the 2 clusters pass through each other. And there's also this kind of hot region that's, bright yellow in the south of the southern core, which might be indicating, potentially some shock heating. In entropy, this bridge is also very nicely visible as an area of very low entropy. So again, this might be low entropy gas that originated in the core that's now located at the northern side of the cluster. And, all of this could be gas that was stripped during the first passage between the 2 clusters. Now, as I mentioned, in these merging clusters, we expect to see a lot of shocks and discontinuities. So we used a number of techniques to highlight discontinuities in the cluster from the X-ray observations. And we found 3 inner discontinuities, north, northwest, and south. And these, we confirmed as kind of very weak discontinuities with Mach numbers of about 1.3. One of them we confirmed as a shock wave. The other 2, they might be shock fronts or cold fronts. But what is very interesting to take away is that these inner discontinuities are relatively rare in these merging clusters. So in general, you do detect discontinuities, but they tend to be located further out in the cluster. And these inner discontinuities might actually be suggestive that we're actually not seeing the cluster after the first core passage, but after the second core passages, the clusters passed again through each other. So imagine that, you know, the set of shocks that are responsible for the radio relics, which you can see are much further out, were produced when the clusters passed through each other the first time. And after, you know, when the clusters started falling back into each other, these new set of discontinuities were produced, which we are detecting quite close within about half of our 500 of the cluster. So, you know, I've been talking about the radio relics, and I just want to kind of show you here some beautiful images that Kamlesh produced from GMRT radio images, and, you know, highlighting to you the northeastern relic and the southwestern relic. You know, both of these sources, they have a lot of properties that are very consistent with them being radio relics. They have steep spectra that we expect, and they're also extremely highly polarized, you know, 40–50%, and in some places even higher. But what was kind of very surprising to us, I mean, surprising, but maybe not so surprising, is that we weren't really able to find a clear sign of an X-ray discontinuity at the location of the shocks. And, you know, while we were bummed about this, it's kind of like they are very far away from the cluster center, and we're really pushing our observations a lot. So we were not able to detect a shock, but we were able to place some upper limits. Like if there was a shock there, okay, what Mach number should it have had for us to be able to detect it as a shock? And this kind of leads to some upper limits from the density expected discontinuity of about, you know, 1.4, 1.5 for the two shockwaves, which is, you know, a little bit lower than what you would expect for radio relics. And particularly from some of our radio observations for these two radio relics, we were expecting much higher Mach numbers. But some theoretical work has shown that you can have this discrepancy between the Mach number you would detect or measure, let's say, in the X-ray and the one measured in the radio, because the radio and X-ray probe different parts of a distribution of Mach numbers, and the radio is just kind of more, let's say, a bias towards higher measures. You know, now that we have some idea about the Mach numbers, one thing that we were interested in was to look at the acceleration efficiency. And what we found was that based on, you know, the Mach numbers that we get from the X-ray, even the ones that we can assume from the radio, irrespective of, you know, which magnetic field assumptions we make, so you know, we can assume that a magnetic field is very large, still, we are pretty much requiring efficiencies that are very, very large. So this kind of tells us that probably these sources, we are not seeing particles that are being accelerated directly from the thermal pool. You have to have some pre-acceleration happening. And putting it all together, both of these radio relics, when we look at kind of their properties, we think that the most reasonable scenario here is that we are seeing reacceleration of particles. Now, in the northeastern relic, we don't really see any like clear AGN that could be, you know, the origin of this plasma that's being reaccelerated by the merger shock. But, you know, we could still have like some ghost plasma, so, you know, an AGN that was active before and since has died, so you don't detect the AGN itself, but the plasma has kind of, you know, spread around in the intercluster medium and the shockwave just reaccelerated it. Or, you know, this multiple shock scenario that I measured, especially if, you know, we have a cluster that has gone maybe through a more complex merger, you could get multiple shots going over the same region over and over. Now, the southwestern relic, in that case, there's actually a head-tail radio source, so an AGN, right next to the relic. So that is like the perfect donor for this plasma. So that part of the problem is, you know, solved, very, very clear here. What is kind of bizarre about the source is that it has this sort of morphology that's inverted. You know, you would expect as the shockwaves travel outwards that these radio relics, they have an arc-like morphology, but it's you know, the arc is kind of pointing towards the center of the cluster. And in this southwestern relic, it's actually inverted. And some models have suggested that you could get such an inverted morphology if you have a more complex merger, if you have, for example, like a subcluster or a smaller subgroup kind of coming into the merger, it could, and it's impinging on a shockwave traveling outwards, it could kind of, you know, disrupt it and turn it into, reverse its angle and bend it backwards. Now, interestingly enough, we also found a very faint radio halo in this cluster. And it is faint, and it also has a very, very curved radio spectrum, most likely. So, some simulations have shown that as the cluster merger goes through its, history, the turbulence kind of goes up and then it's like it starts going down. So these kind of very faint radio halos with very steep radio spectra are generally expected to be associated to these clusters in an inefficient acceleration phase. So this is indicating that this cluster might be in a very old, very evolved merger status. Now, just very quickly, I wanted to kind of place this cluster in the context of other clusters that have been studied. And, this is showing you a very well known correlation between the power and the mass. So the power of the radio relic versus the mass of the cluster. And you see our radio relics here, they just fall on the correlation, nothing special here. They're also, reasonably sized given how far away they are from the cluster center. So you would expect, the shocks to become kind of bigger and bigger as they move outwards. But, where this cluster is really special is how far away these relics are, given how small the cluster is. So actually, they're the most distant radio relics that we know of. And this is actually just the projected distance between them. And we have multiple lines of suggestions that actually the merger might not be happening in the plane of the sky, but it might be happening at 45 degrees, which actually places the physical separation between the radio relics at 3.6 megaparsec. So very, very far away. So this is very, very interesting. And, it helps us pose a lot of constraints on the merger scenario. And the idea here would be, as the cluster kind of fall into each other, then they separate, they reach epicenter, they fall back in for a second merger. If you look at these different snapshots here and kind of how our cluster looks like, the most likely scenarios are that we are, somewhere here before the second core passage or right after the core passage. And, this can help us explain these, this faint radio halo, which you expect if the cluster is quite old and evolved in its merger history. It helps us explain the small distance between the X-ray peaks of the two subclusters, while also explaining the very, very large distance between the two radio relics. So, if you wait, more time passes, the shock waves have time to move outwards. It could also, especially if you are seeing the clusters after the second core passage, you could also very nicely explain these inner discontinuities that we see that could be associated with the second phase of the merger. So, as I started this talk, I was sharing you how we have this limited number of clusters with diffuse radio emission at masses below 5 times 10 to the 14. And, this is really kind of an observational problem. Just our telescopes haven't been really powerful enough to be able to detect this very diffuse, very faint radio emission. And, with these new generation radio telescopes, we may just be, this might just be the tip of the iceberg. And this PSE cluster might actually be representative of a broader range of clusters with diffuse radio emission that will be detected in the future with new sensitive instruments, all posing a very firm challenge to kind of our expectation that particle acceleration might not be very efficient in these low Mach number shocks in low mass clusters. And I think this shows how powerful the SKA, for example, will be, particularly, in combination with Athena, fingers crossed that everything works well, and both these instruments are going to be used together because they're really going to be a game changer for, detecting and understanding the origin of these diffuse radio sources in low mass clusters. And with this, I will say thank you so much. Apologies, I was a little bit long. I promised I wouldn't be, but I was. And yeah, thank you for the attention. Welcome any questions.
Questions for Andra?
There's a question behind you.
So you said in the beginning that these large radio relics, they don't have any counterparts in the optical or other wavelength. My question is the following: can they affect the unfolding galaxy population somehow? Like, for instance, if a galaxy, star-forming galaxy, on its first passage crosses this front, will you see any changes? Do you expect to see any changes? I don't know, increase in ground pressure stripping or
Yes,
ground pressure
yeah.
or something like this?
Yes, so I started my career as a radio astronomer, and then I got interested in galaxy evolution, and the body of work that I haven't talked to today deals with exactly your question. How do these kind of mergers and all of the, tidal, very strong tidal fields, shocks, turbulence, how they might affect the evolution of galaxies. And from my work and some other work from other groups, what we are seeing is that in general, these merging galaxy clusters tend to have increased star formation. It's probably a combination of, as the two clusters come towards each other, they tend to have most likely filaments, which kind of captures a lot of gas-rich galaxies in between. And those are just kind of, ripe for one of these, shocks or one of these non-thermal phenomena to kind of come in and act as a catalyst for star formation. So a very long-winded answer to say yes, we do expect to have an interaction, and particularly there's simulations that have looked specifically at what happens when you have a shock going through a galaxy, and it is very, very similar to just the ramp pressure that a galaxy experiences as if it's falling kind of very quickly into the cluster. So you would expect very similar effects to like a jellyfish, and yeah, exactly, yeah.
Any other questions? Or online?
Nice, very nice talk, thanks. So is it still related to the energy budget? Could one compare the fraction of the energy into the accelerated electrons at both the discontinuities or the internal X-ray shocks with the radio and see if there is a time evolution? So, for example, the energy into the electrons emitting a radio fraction is smaller than the one in X-rays or not, compared to the ramp pressure, for example, which is essentially the total energy source.
Honestly, I have no idea. I think that there are people in the audience that probably would know the answer to this question better than me. But I would need to think about it because I haven't really worked on energy budgets that way. I feel like that's a little bit more of a theoretical question that's outside of my field of expertise.
So when we measure this in the interplanetary shocks and heliosphere, for example, or also when we try to infer it for the superlunar shocks, we see that for the ions, that's about 10%. So 10% of the ramp pressure goes into the acceleration of the ions, and somewhat slower in the electrons, although there are cases where electrons eat up a comparable fraction of energy. So, yeah, just I was interested if one can see an effect of time evolution comparing this, because you said X-ray shocks are younger, no? The discontinuities in X-rays, more internal, are younger, more recent.
So, I'm not entirely sure I understand what you mean by younger here.
Generated after the second iteration of the collision.
So the inner discontinuities in the center, yes, we expect them to be, as you say, younger. We would expect to see a discontinuity in the X-ray, also at the location of the radio relics. The X-ray data is just not deep enough. We're limited by systematics, but that would be kind of the golden, like the hope that we would have would be if you had like perfect X-ray data, you would expect to detect it in the X-ray.
Yeah, probably you don't see the external X-ray also because the synchrotron loss is much smaller. No?
Oh, you're thinking about the radio emission associated with the shocks in the center, you mean, or?
Yeah, comparing the two. So the radio outside with the X-ray inside. So they are both emission from some population of energized electrons, which have a different story. So they drain a different amount of energies from the ramp pressures inside and outside.
Yeah, I would have to think about it because I think, I guess the complexity, I'm not an expert in this, but one of the complexities you have is obviously this is all kind of happening on top of the thermal emission from so I think you need to model that out, and I'm gonna say we have in Chandra 3,000 because I probably want to do this with Chandra because it has better resolution. We have 3,000 photons across the entire cluster, so it's tough from that perspective.
So if I understood your recall correctly, there's some possibility that these objects are partially fueled by jets coming from an AGN in the center of one or more of the clusters. So is this always gonna be a problem? Is there always some ambiguity between the double load radio source that may be caused by a giant AGN in the middle of the cluster at this effect?
No, that's an excellent question. So the way that usually you could tell the difference is by looking at the resolved spectral properties of in the radio, for example. And I actually have a slide that might help with that. Sorry, let me just exit so that I can find the. So let me, no, maybe not this one, this one. So in, this is just showing you spectral index, so kind of what the slope of the radio emission is, let's say pixel by pixel. And let's, focus on this one. This is a bit smoothed out, but usually if you had like, let's say you would have an, AGN here. The spectral index, for example, if you had like an FR2 or something like that, you would have like a very flat spectrum where you have the hot spots. And then the spectral index becomes steeper and steeper because the plasma is kind of move backwards. And then you kind of have the older plasma away from this active point of particle acceleration. In radio relics, you actually expect to see, because of the way that the shock moves, you actually expect a very different gradient of spectral index. Here, the shock is moving this way. And this is kind of what we're seeing. You see red is very flat emission and blue is very steep emission. So in some of the kind of most, let's say, well-behaved, simple objects where we have a lot of good data, you see a very, very nice gradient in spectral index, which tells you that even though maybe the emission was previously pre-accelerated by AGN, this shock front is the thing that's going to leave a clear imprint on the spectral index, and that's kind of how you can tell.
Any final questions for Andra? Okay, so I take the privilege. So can you tell us whether the combination of these multi-wavelength information can tell you about the structure of the magnetic field in the relics, and like the coherence lengths and the strengths, and how might these compare with the radio halo?
So in terms of, I think the most powerful component to this is the radio. If you have good data, you can do a polarization analysis, which we've done. People have tried and possibly detected like inverse Compton from the X-ray, but not in this particular cluster. We maybe, have one detection that I've heard of in clusters. In terms of the actual, and that could, assuming equipartition, that would give us an idea of the actual strength of the magnetic field. Otherwise, we have a little bit of we can't really tell. You either like the spectrum can become in the radio can become, for example, steeper if you have a stronger magnetic field, which leads to more losses. So there is a bit of I'm missing the word here, but you can't tell them apart is what I'm trying to say. So you make some assumptions based on simulations of kind of what is reasonable. You're not going to expect to see, 100 Tesla or something in terms of magnetic field strength. Now, in terms of kind of the more detailed part of your question about like coherence length, things like that, I'm not really an expert in that, but maybe I can come back to you. I can talk to like Paola is really an expert. When it comes to Paola Dominguez Fernandez, she knows a lot about magnetic fields and polarization, also kind of from the theoretical point of view. And Kamlesh is also a very good person to talk to.
For example, you can check the rotation measure distribution from
Yeah,
polarization, and from that you can also get the indirect estimates on magnetic field strength and also coherence length. So there are, for example, in Andra's paper, we also present rotation measure maps, and on the basis of standard deviation in rotation measure value, you can, like assuming some assumption, you can estimate the magnetic field strength, which is in clusters typically 2 to 5 microvolts.
Okay.
Yeah, but it's all very I mean, even the X-ray would be a relatively because you still need to make some assumptions. It's very difficult. I don't know of any way that we would, really get a direct measurement of
Yeah.
this. Of
No,
this
no,
strength.
yeah, I was, to rephrase my question, I was mostly curious as to, the difference in magnetic field strengths that you expect from the radio halo. So as you go out from the cluster, system, you expect this to decrease to like 10⁻⁻1 microgauss as you reach like megaparsec scales. But then you have these, features. So like, what's the average magnetic field strength that you would expect for a relic like this?
Yeah, so these are the numbers that, Kamlesh, so you do expect,
Yeah.
yeah, and you do expect, I think there's some models that say that they predict that you would amplify the magnetic field as well at the location of the shock.
Okay.
So, I think, maybe the magnetic field would do this and then it would go back up. There's some work, I mean, I know of coma, but I don't know if there's any other where people have used, background sources, Faraday rotation to try to get the sort of profile for the cluster, but it's tough.
Using actually background sources, so you can get the
Yeah.
radial profile, but it is assumed because radio halos are unpolarized.
Yeah.
So observationally, we don't know, but it is expected theoretically, according to our models, that is decreases radially, also magnetic field.
Yeah. Thank you.
Thank you.
Thanks a lot. Let's thank Andra again.